It's like, isn't it obvious that all pi bonds you cannot rotate about a pi bond? So what's the point of having the first condition? Isn't it understood? True, right? Correct, right? The first condition is understood. The second condition is what is really important, okay? Let me illustrate. So we have the cis here. Can you stop eating and dropping on the floor? Okay, this is cis. I'm going to construct a constitutional isomer of this. Constitutional isomer is like Lego like that. You plug out a bond and you plug it in elsewhere on the parent chain. So this is a constitutional isomer of just now those two guys, the cis and the trans. This is a constitutional isomer. This doesn't show cis nor trans. Why? Because even if you are allowed to break the pi bond, even if you rotate all you care, there's no difference whether you rotate or not. True, right? So that's why we have the second condition. I will say it in such a way that each of the two groups, write it down. I say it in a more precise manner. The second bullet point, the condition, I say it more precisely one. I will say that each of the two C's, right? Each of the two C's in your CC double bond are bonded to two different groups. So we are not comparing like that. We are not comparing like that. We are comparing this versus this and this versus this. X is indeed different from Y. Good. And W is indeed different from Z. And hence this thing shows cis trans. So examine this. Why doesn't this show cis trans? This what did I do? Oh, actually both violate cis trans. I mean both won't allow you to have cis trans. Both carbons. Green is equal to green, yeah. Fail already like your condition 2. On top of that, this guy, your red equals to red. So both carbons actually disobey condition 2. So that's why I don't have cis trans. But you only need at least one of them to disobey in order not to show cis trans. So let me erase away my red and replace by maybe white. Get the point. You only need one of them to violate condition 2 in order for the CC double one not to show cis trans. Get it? This guy is the culprit now. Because of this, it doesn't make a difference whether you can break the pi bond and hence rotate. So can? This is saying both of them, each of them must have two different groups each. Whereas in order to violate this, I only need at least one of them to violate it. Clear? Logic. Like this example. Okay, can people?
Does that mean that like a molecule that will never exist?
How can it not exist?
It will exist but not as something.
Yeah, it will exist on its own, there's no cis trans of it lah. But take note I go and plug out and plug in again. Is this cis or trans people? Let me test you. Is this cis or trans? Yeah, look for the same group on each carbon and check whether are they on the same side of the double bond, which they are indeed. It will be called cis. If they are on diagonally opposite the CC double bond, it's called trans lah. Don't listen to the nonsense he teach on page 24, I think. Page 24, you see what big group, small group, he's confused with another sort of naming. Yeah, he's confused with some other system. Just ignore it lah, This is really trans. Don't care about big group, small group. You never even define what you mean by big and small. You think what? Idea? Okay, so right, the conditions, people, only second condition is important actually. Because the first condition is like 讲废话. Isn't it obvious? Yeah. So if you go back to my list here, right? If you go back to my list here, what do you need to know how to do? You encounter a CC double bond. Is there cis trans? You use the conditions to check. If there is, draw a label, like what I did here. Right? So you'll be tested on Monday on this skill 2. Actually, implicitly it's also skill 1 now, correct? Can people? If it doesn't show cis trans, then what? You need to explain why it doesn't show cis trans. This guy doesn't show cis trans, sorry, I need to plug back. This guy doesn't show cis trans because of the carbon pointing down. The black guy pointing down. This guy nah.
Pointing down?
No, it's my orientation. It's due to this carbon, that's why it doesn't show cis trans. It's not due to this. Can I was in this orientation just now, but it depends on how you draw also. What? Can people so yeah, why doesn't this guy, for example, show his trans? You need to know how to explain. And lastly, point 4. This one you need to listen carefully. Point 4. Point 4. Given x n, I use the capital letter M, I use M, right? Given m number of CC double ones that can show cis trans. Notice I stress the word can. I never say just number of CC double ones unrestrictedly. We are only considering the number of CC doubles that can show cis trans. Our total number of stereo isomers will include about n. Let me explain to you where this formula come about. You know, an alkene can either be cis or trans. Let's just say you got a second alkene down the line. Whether it's cis or trans, the second guy, whether it's cis or trans, doesn't impact whether the first one is cis or trans, right? Actually, they are mutually independent events, right? It's like throwing a biased coin twice. How many outcomes do you have? 2 times 2, 4. Then your third alkene, whether it's cis or trans, really not affected by whether the first 2 are cis or trans, right? So you times another 2, so altogether you got 2 to 3, 2 times 2 times 2, correct? So you want to generalize, you've got m number of such CC double ones. The total number of stereoisomers will be 2 to the power m. Get it? Understand? It's a probability type of thing. Clear? Understand where this thing come from? So give me an example, people. Give me an example, 2 to the m. I'm just going to create an alkene with 2, what do you call it? Oh, actually you can use the example. That one cannot. That one only. So I just give you an example of 2 alkenes, then it's like that one. Correct? These 2 alkenes can show cis trans, correct? Anybody trans or cis? It's trans. Look carefully, it's trans. This guy is trans. So, yes, there are actually theoretically 4, right? Cis cis, trans trans, trans cis, cis trans. So I draw all 4 for you all now. Trans, cis will be the next that I'll be drawing. Trans, cis. Right? Trans, cis, trans, cis.
It's on the same.
Okay.
It's on the same thing.
Then the next one I can draw is cis cis, right? Correct? Cis cis. Cis cis. And the last one that I haven't drawn yet is cis trans, right? Cis trans, the first one being cis, and the second one being trans. So these are the 4 different forms of it. Yeah. All the way out of 4. None of them are the same. You got 4 mutually different stuff there. Can you see why is this cis and trans in the first place or not?
No.
Okay, this is trans. With respect to this is trans because your H and your H are diagonally opposite the CCL1. That one can see it or not?
Why the other H don't?
This is called trans, right? That's why I tell you all need to recognize your skeletal diagrams, right? So this is double trans, trans. This is trans, correct? Cis. Got it? Oh, this is cis, cis. Oh, this is cis, trans. Look out for the same group of atoms on each carbon. Check whether are they on the same side of the double bond or are they on diagonally opposite sides. Can? So, got it, huh? Well, understand how I designate all these things and you go and build some models, you realize that all 4 of them are different stuff. Okay, Ken, so I'm explaining the formula here. You got X number of CC double bonds that shows cis trans. Your total number of stereoisomers is 2 or X lah. Okay, so that's point 4. Okay, shall we go on to the second class of cis trans, which I will just say in passing only. The second class, which is this class here, this one here, second class, it still involves CC double bond. But just now CC double bond is not involved in the ring. Whereas now this class here, we are involved in the ring. Can you refer to page 25 of your notes now, right at the bottom part? This part here, Hua Zhong will teach. Other schools usually don't teach. And the good thing about hotel is they eat properly. Okay, so right, if you go to page 25, right at the bottom there, do you see your alkene as part of a 8-member ring? Okay, can you see that cis? Because there are 2 H's, I'm just pointing out. That's cis, right? The one on the left. And then you see the very weird looking guy on the right. That's actually trans. Do you notice they shaded the other bonds? You all know what they're trying to say? It's actually above the plane of the paper. All the CH2s are above the plane of the paper. Let me explain what I mean by all these words here. Okay, it will only show cis trans if the number of carbons in your ring is more than or equals to 8. See, your alkene is here. Your alkene is here, then you can go and force it to be trans. And the rest of the carbons are okay. Let's just talk about cis first. That one easy to say. Let's say your alkene is part of a ring. Your other carbons can happily just be like that, right? Correct?
Yeah.
But now let's talk about trans. You go and trans like that. Certainly, I mean, you can like that lah, but the point is your angles will not be the same. It won't be fair to some of them. It won't be fair for some of the bond angles. So as a result, right, your other carbons need to like that above the plane. But if your ring size is too small, all these CH2s will jut into the pi electron cloud here, right? Then it will cause strain within the molecule. It won't be stable. That's why the size of the ring has to be big enough in order to adapt to your trans. Understand the concept? If there are too few carbons, the rest of the carbons will jut into this guy's electron cloud, pi electron cloud. Then it will cause instability. Clear? So in order for trans to exist in a cycloalkene, you have to make sure that the ring size is really big enough for all the CH2s to avoid this guy, for the thing to be stable lah. Can? Understand the idea?
Why would they need to avoid?
Because electrons repel each other. Can? Your size cannot be too small, and then evidence has shown that 7, when your ring has 7 carbons, the trans still doesn't exist. Only when you go on from 8 or 9 or 10, larger than 8 or 8 then they have proven it that such a thing exists the one on the right. Okay, then you notice, okay, understand the idea first? The ring size, it has to be as big as possible in order to avoid strain within the molecule. And then for your information, do you realize they draw 2 pictures here? Do you know what it means? How come they draw 2? Why don't they just draw 1? That's because these 2 are actually a pair of enantiomers. They are a pair of enantiomers. Why are they a pair of enantiomers? Because there's no internal mirror plane cutting through any of the molecules, which I will be talking about later. Enantiomerism is caused by the lack of an internal mirror plane. Enantiomerism is caused by a lack of internal mirror plane. Mirror plane. Okay, can people? So for your information, these are a pair of enantiomers. Why do they exist as a pair of enantiomers? That's because you just look at any of them, there's actually no internal mirror plane. I can't build the model for this. This is very high tech. All these things, I don't have enough holes to. Maybe I can try but I just take note When you got a cycloalkene, the cycloalkene part can only show cis trans when the ring size is larger or equals to 8 carbons big. Yes, and understand why Because if you don't understand why, what's the point of learning it, right? What's the point of just learning this part if you don't understand what it is? In fact, if you don't understand, you're not learning anything. So that's the second class of cycle of alkenes. Alkenes not in a ring, the ones there, like pentoene. Alkenes in the ring, actually it's not drawn at all. We go on to another type of cis trans that doesn't involve any CC double bonds. We go on to this family here. It just involves rings. Without any CC double bonds. So now, y'all can a lot clear? Let me explain how using this. I need to build another one. I need assistance. Don't plug everything. No, don't plug anything. No, just unplug the flexible ones. No, don't. So, like that. We are drawing, I'm trying to build a cyclobutane ring, a 4-member ring. You can see the square in the center, right? But bear in mind, you might want to take note, this type of thing, right, actually doesn't depend on the size of the ring. It can happen in a 3-member ring, it can happen in a 4-member ring, it can happen in a 5-member ring. The size of the ring really doesn't. Where's my flexible bond? Oh, don't have. Can you look? Is there any flexible bond?
Have you seen my
Oh my! Look for it lah. I need the bond back.
It's not there.
Not there. Oh, it's no, cannot. I still need one more. Okay, maybe it's in this box. Oh, it's here. I accidentally put it back inside here. So right, I'm building a I don't need this blackboard anymore. So I'm building 2 cyclobutane rings. Okay, 4-member ring. The black balls just mean the 4 H's, the 4 carbons. And then white just means the typical hydrogen. Oh, it's actually here. Oh, I don't need it anymore, so I got it out. Okay, again, so
I'm trying to get like a proper angle.
these things are quite expensive. It costs about $100 per box. Wow. Yeah, I don't know why it's so expensive. Maybe because it's from UK. It's not very expensive. Okay, people. This is cis. Let me explain to you why later. And this is the trans. Basically, your red and your green balls represent different type of groups. And then your whites are all your hydrogens. This is called trans. How do you see it? Look at this angle. Imagine you got an equal sign down there. Can you see there's trans?
Yeah.
And this is, although it's not very flat, because I twist the bond until like that already. It's cis, can? Now, right, can you go to page, don't know what of your notes, can you go to page? Oh yeah, it's page 25 on the notes. Page 25 on the notes. Do you see the note here? What he's talking is total nonsense. Here, this line here, can you cancel this line here? I will tell you what to replace later. My finger here.
Like the one you're covering or the one
Free rotation.
Cancel the entire paragraph now. You all will learn the wrong stuff. You all get more confused when you read it. Correct, Donnell? Okay, let me explain the proper way of explaining this thing called restricted rotation in the cyclohexalkane ring. I follow his way on numbering. Is this carbon is called 1, is this carbon is called 2, is this carbon is called 3, is this carbon is called 4. 1, 2, 3, 4. The correct way of understanding the idea of restricted rotation is, let's just say we are allowed to break the C1, C2 bond, which is this guy that I'm breaking. Now that this guy is broken, now you can rotate freely along your C2, C3 and your C1, C4, right? Yeah. Rotate all you can. There won't be any difference between cis and
It's not the free rotation.
trans. Cis and trans.
Can the other one also? The other one rotate like this one?
Yeah, you can rotate, it's just relative.
Okay.
So get the idea? It's about whether you can break the C1, C2 bond or not to allow free rotation about C2, C3 and C1, C4. What he's talking here is total rubbish. I also don't understand what he's saying. You can't rotate about C1, C2 anyway, what? What is he talking about? You can't rotate about C1, C2 anyway. And then his word then is like, he's putting the horse in front of behind the cart rather than in front of the cart when he uses the word then. The logical order is the other way around, eh? Even if it's breaking the right bond, but it's like two errors. First is logical error. Secondly, his bonds are wrong one. The one that's supposed to break, he never break. He got to rotate. The bond that's supposed to rotate, he got to break. It's just one big mess, might as well just cancel out these two lines, right? Correct? You all can understand now, people? It's about being able to break C1, C2, and hence you can rotate about C2, C3, and C1, C4, but there's no need to rotate both at the same time. You just rotate one can already, you get the point. Donnell, are you very... You see what nonsense is he saying? I don't understand when I first read it. Then my conclusion is just make one big mess. The remedy to this is just cancel this thing out and then write out what I write. So if we can break C1, C2, right, then there can be free rotation. There can be free rotation about C2, C3, or C3 or C1, C4 bonds. Then, right, as a result, your cis is indistinguishable from trans, correct? But the problem is you can't break any bonds. That's why your cis and your trans will be two different things. Can is what I just explained. If we can break this, we can rotate about here or here. And this thing won't be different from this. Get it? And hence this cis-trans isomerism won't exist, right? But the problem is you can't even break anything. Wow, the way you write. It's even worse than putting the horse behind the cart. It's more like putting the horse under the cart or something.
Under the cart.
So you can buy one set of that for $14.
Never mind, I just can run out. Can? So get the idea here, it's talking nonsense, so amend it for yourself. Don't learn the wrong thing. It's like reminds me of some Kung Fu novel like that. I don't know whether you got watch Legend of the Condor Heroes. Yeah.
Oh shit, I was old school, man.
Then it's
Wait, Joel,
then
you
try
watch
to the smart woman go and trick the evil villain, some martial arts manual, right? Kung Fu manual. Then she go and dictate to him the other way around, and then he go for went crazy. Yeah. All his acupoints all like much there, then he went crazy. Yeah, that's an example of that, right? Anyhow one now. Logic totally the other way around. The type of bonds you supposed to break, but you don't break, you go and rotate. You're supposed to rotate that bond, then you go and break. Then what's he doing? That's what is he doing? So anyway, yes, write this is the correct form of it. Can people? So we actually covered the three forms of alkene, cis-trans. Alkene not in a ring, the most commonly tested. Alkene in a ring, there's a severe restriction on it. Your ring must be more than 8 carbons large. Can? And the third family, which is the one I'm talking about now, in a cycle alkane ring like that. But please be careful of the way he explains, it's wrong one. Can?
Yes.
So we are done with cis-trans already. Any questions?
What do you mean? Why can't you break? You can't break it.
Commonly tested is alkene not in a ring. And this type of case. And I can tell you what's commonly tested. Usually for promos, they don't try a few people. They will test alkenes not in a ring. The one that I just drew, remember? And 2 in cis and trans. But I honestly don't want to give you exactly the same compound that they are going to test on Monday.
Wow. Spicy.
Can I carry on now, people? Okay, now right, can we go on to enantiomerism? Which is this. Not page. I think you read page 23 or 25 yourself already. I explained the gist of it. Restricted rotation about what, make sure you know how to draw and label properly, etc. etc. All the 4 skills are listed on page 9 of my notes. We don't waste any more time. Maybe we just. Oh, page 26 is talking about the formula. Yeah, page 26. What I call the 2.m formula is what he called 2.n formula. Doesn't really matter whether it's 2.m or n, as long as you know what exactly your m and your n is in that context. Doesn't really matter what symbol you use. Okay, people? Then right, we go to the second major class of steroid isomerism. We talked about cis-trans already. we go on to the second major class, enantiomerism, page 26, somewhere down there. You can just ignore this part, it's talking nonsense. No, you can just ignore this part.
Oh, but he said it was important.
It's important because he thinks it's important, but things that he thinks is important might be total rubbish, like that part there.
So we can still use optical ICs.
I don't know about other schools, but he said you can only use enantiomers. I don't know about that. Okay, can I go on to the concept now?
Yes.
If you look at my page 9, right, there's a very long list of it, of skills you need to learn. Page 9, this part here, this entire section here. Let me go through point by point, okay? But then again, you will notice I jump here, jump there because they are all interrelated. I try my best to make it in a logical order, but because they are interrelated, I might jump here, jump there. Okay, let's go through the fundamental concept. Just like we studied the key cause of cis strands due to restricted rotation about a certain type of bond, whether it's a pi bond in a CC double bond, or whether it's a certain bond in a cycloalkane ring like this now. Now we think about the key cause that causes enantiomerism. Okay, you're going to read this thing here. It's the lack of an internal mirror plane. You all know what's internal, right? And internal means it's inside the molecule, while a mirror plane is a plane that divides the molecule into two equal halves. That's what you mean by internal mirror plane. Okay, let me give an analogy of this thing called enantiomers in daily life. Know your left hand and your right hand. There's this thing called a left glove and a right glove, right? You can't wear your left glove on your right hand and your right glove on your left hand. You can't, right? Your hands are handed, yeah? And the word chiral means handed. Okay? The word chiral means handed. Do you see any internal mirror plane in your hand?
No.
Good. Anybody disagree? There's no internal mirror plane in your hand? No, right? Your left hand is the mirror image of your right hand. Because you got no internal mirror plane, your mirror image will not be the same as yourself. That's the fundamental concept behind enantiomerism. You are not allowed to do this, people. This is not. You can't do this. This is actually just generating a mirror image, you know. Can or not?
What is internal mirror?
It's a mirror plane that's internal. That's inside the thing. Okay, Ken? Your hand does not have any mirror plane that is inside it, yeah? So therefore, its mirror image will end up not the same as itself. Agree? Your left hand is different from your right hand.
Yes.
Your ears are also different. Your left ear is not the same as your right ear. Agreed?
Yeah.
There's really no internal mirror plane cutting through any ear. And that's why there's this thing called a left ear and right ear, right? Okay, going on to molecules. Now you know this is trans, right, people? Hey, look here. This is modern concept. This is trans, right?
Yeah.
I'm going to build another trans for you. In fact, I'm going to build a trans as a mirror image of this. I just hazard a guess. I can't remember. I really don't know whether it's a mirror image or not. I just anyhow change. Is this the same thing?
Yeah, isn't it?
No, it is the same guy. It is the same guy. It is the same guy. So I built one guy. It's the same thing, so I need to swap. Okay, now I'm building a trans. Can you see the transness here?
Yeah.
And this is a fellow trans. Are they the same thing? Look carefully. They are not the same thing. I think I twist the flexible bond until it's single already. It doesn't look like square planar. It's flat anymore. The 4 carbons. But anyway, you are convinced both of them are trans, right? But both of them they are actually not the same guy. You just superimpose the black and the whites together, yes. But the problem is you cannot superimpose your green on your green. You can only superimpose your green on your red and on your red on your green, vice versa. They are not the same thing, agreed?
Yes.
Yeah.
Why? Because is there any internal mirror plane in this guy?
No.
No, this is not an internal mirror plane because red doesn't correspond to green and green doesn't correspond to red. There's really no internal mirror plane, right? Hence, its mirror image, which is this. Let me just orientate to look like its mirror image, yeah? Can you see the mirror? The mirror is actually here. Because there's no internal mirror plane in this, the mirror image of this, which is this, will not be the same as itself. And this is the fundamental concept behind enantiomers. We are going to say that these two are a pair of enantiomers. Yeah, no, that's a fundamental concept. Okay, Tonya, you go, are you, what, Ken? Yeah, chirality is the Greek word for handedness. That's why I use hand as an example first. No internal mirror plane. The mirror image, which is the other hand, won't be the same as the same hand. Won't be the same as the original hand. Okay, in the world of molecules, this guy here, really no internal mirror plane. The mirror image is actually not the same thing. They are called a pair of enantiomers. Okay, and of course there's the cis guy lah, which I dismantled already lah. I don't have enough flexible bonds. Okay, Ken, so understand the fundamental concept, Okay, now we go on to from chiral molecules, right? Maybe we go on to chiral carbons. What's generally Yi-Ching okay or not? Okay, I need to build this again. Your blue ball is the chiral carbon now. Your blue ball is a chiral carbon. It's a carbon, while your other four colors are just four different groups. Okay, then I'm going to build something else. I dismantled already. I just took up try. I tried this, and then okay. First question: is there an internal mirror plane anywhere?
No.
Four different groups, yeah? There's no internal mirror plane. So you expect the mirror image, which I hope this thing is, I just anyhow build. It's actually the same guy, right?
No, it's mirror, it's a mirror.
It is a mirror image,
Yeah.
So let me just orientate to convince you that it's indeed a mirror image of each other.
Oh.
Can you see they are not the same thing? Eh? Oh yeah, correct. Yeah, they are not the same thing. So I prove now if I were to change one of these groups to a white, or maybe I change one of these groups to a green. Now how many different groups have you got on the C? The green, the white, and the black. Can you see that there's an internal mirror plane cutting through here?
Yeah.
The mirror image will be identical to itself. So now you know what's a chiral carbon, right? A chiral carbon is defined as one with four different groups. I mean, only when you got four different groups, then you won't have any internal mirror plane cutting through that carbon, and therefore that carbon is defined as chiral. Clear, people? So we go on from chiral molecule to chiral carbons. What?
What is this part talking about?
The same thing. If you rotate this one, then we superimpose on this.
You're talking about notation part, is it?
No, I don't know, like, then it takes the same equals to
This is rotate equals to this one, then you cannot superimpose. This is what equals to this one.
Oh.
Yeah, that's what he's saying. You can actually play the models to see what he's saying here.
It's like this one, they one and the mirror, they like stacks it.
Okay, got it. Chiral carbon is defined as four different groups.
Then it's not the same because
Now, people, go back to this. Go back to this guy. The black guys are chiral, okay? Four of them there are four carbons in this ring, right? Is this four different groups? No, right? It's two whites already. Two out of four are the same, so this is not chiral, neither is this chiral. But you realize that this carbon is chiral?
yeah.
First group, green. Second group, red. Third group, black, green. Fourth group, black, white.
Oh, it's kind of like that one.
This is chiral, and so is this chiral.
Oh.
Hold on.
Yeah. Even when you're talking about the cis form, right? These two carbons are still chiral, right? Okay, now let me go through slowly again. How do you count the 4 so-called different groups per black ball? Okay, do it slowly. I almost broke the thing. With respect to this carbon here, first group green, second group red. That one no dispute one. Third and the fourth group you need to listen carefully. Third group is a C, is a black, green, red. Fourth group is a black, white, white. They are different, right? So therefore this thing is chiral. This carbon here that I'm holding on to is chiral. By the same logic, this carbon that I'm holding on to here is also chiral. First group is a green, second group is a red, third group is a CH, C white 2, black white 2, black 2 whites, and the fourth group is a black, green, red. Get it? Therefore this is chiral.
So you only look at the immediate carbon, like to the carbon.
No, the idea is
you don't look at the whole thing.
Okay, give me another example. You all must understand this first. Give me another example. This guy here is also chiral, although on the surface some people might think it's not. This carbon is chiral, okay? This carbon is chiral. First group is a H, which I don't need to draw because this is skeletal, right? Second group is a Cl. Third and the fourth, pay attention. People might think it's the same because it's CH2 versus CH2, correct? But you cannot see like that. You have to actually carry on per group.
Oh.
Is this the same as this then?
No.
CH2 is not equal to CH3H, right? So therefore indeed the third and the fourth group are different, therefore indeed this is chiral. You cut until when you terminate at the same point. Or when you terminate all together. Yeah, so give you another example. I just give you a very long thing here. A very long thing here. Sorry, I just destroyed my felt.
Unless you reach the end and it's so different, that means it's not.
So like that, then CL, 1, 2, 1, 2, then this guy VR, then this guy is just an OH, then this guy is a H lah. Then we are focusing our attention on this guy. First group is an OH, second group is a H, right? Third group and fourth group, don't think they are the same because they are not the same. You can't just conclude CH2 equals to CH2, therefore these two groups are the same. No, you have to carry on. CH2 equals to CH. No, you are still not supposed to stop there. You are supposed to see until you see a first point of difference, if there is. Wait, later, that one, I don't talk about rings first. I just talk about open chain type of things first. Can people? So the guy that I dot in the center is actually chiral. Don't just conclude at the CH2 stage. You need to carry on looking for the first difference until, basically how I said it yesterday. Let me send what I sent to Elias from SB9. He was confused about this. If I were to give him this yesterday, he would think that this is not chiral because to him CH2 equals to CH2. Then this is what I replied to him. Elias, let me just WhatsApp you all what I wrote to him.
Both are CL, then it's chiral. But it's supposed to continue until you see a point of difference.
Okay, if you want the entire message, you can kind of look at my handphone now.
Yeah,
If you want the entire message, the entire context, you have to continue looking along each group until you reach the end of each group or you reach a difference between the groups or whichever case you arrive at first. So that's how you say it. Well, of course you're going to say it in exam. The skill that they want you to know how to do is in exam is you need to identify whether a carbon is chiral in the first place or not. Okay, don't need to say these words. The idea is there. Understand? So this guy is actually chiral. Don't stop here. Don't stop here. You also stop here. Again. Okay, so what we have been doing so far is explaining the concept behind here using hands and ears and other stuff. Then here, we'll be doing this tomorrow lah. It's under here, under all these bunch of questions here. Or you want me to do it now? I can also. Can. Second skill is, first skill is here. Okay, can people?
Yeah.
I go through everything one shot tomorrow, is it? Is that what you all want?
No, but we can we finish as much as we can?
Go through the questions, is it?
Yeah, go through a few today.
Okay, maybe we go on to look at questions 18.
Because if you do tomorrow, I skip it.
Okay, people, maybe we go through questions.
After GP.
Question 18. Hello, can you go to question 18 in your tutorial? Okay, 18, my advice to you all is, if you all got time, go and practice your skeletal. if you find that you spend too much time drawing skeletal, I strongly advise you against you drawing skeletal for this question. But honestly, when you draw skeletal, it's more obvious whether it's chiral or not. Okay, when you look at this, it's not that obvious. Now let me translate A to skeletal. It starts with a Cl, correct? We go on to a CH2, agree? Can. Then we go on to a CH, which is bonded to an OH. And we go on to a CH2, and we conclude with a Cl.
Hey, sorry, sir. Is it necessary if you were to write out that what's that thing called? That formula, right? Do we need to put the bracket?
You can.
But if you don't put, is it okay?
It can be confusing if you don't put the bracket around your OH. Hey, can people?
Yeah.
Can you see that the carbon here, is it chiral or not?
No.
Good. Isn't it more obvious when looking at this?
Yeah.
But the issue is whether you spend a lot of time drawing skeletal or not. If you find yourself spending a lot of time drawing skeletal, then my advice is just look at it like that. Okay, if you draw skeletal very proficiently, it's actually best to translate to skeletal first, where you can see whether that carbon is chiral or not. Why don't you consider these two carbons, may I ask? Because they are CH2s. You don't consider this as chiral because it's a CH2. 2 out of 4 groups are already the same. How is it chiral? Remember 4 different groups, right? Don't consider this, don't consider this. This is still up and running, but problem is it's not. Because your third and your fourth group are exactly the same thing. So A doesn't have chiral carbon, the answer is A. Can people?
Can.
We go on to the rest, we identify where the chiral carbon is. Maybe I just cut a long story short. The chiral carbon is actually this guy. The chiral carbon for part C is actually this guy. And the chiral carbon for this is this guy. Okay, so oh yeah, another thing people, it's not just identifying chiral carbons. That's what we are doing now currently, correct? It's also drawing your pair of enantiomers. You need to know how to draw. Okay, shall I demo how you draw?
Yes.
Okay, I'm actually talking about this skill here. Drawing all the enantiomers, in this case there are only 2. Drawing all the stereoisomers, in this case there are only 2 enantiomers because there's only 1 chiral carbon per option. Okay? And recognize, that's provided you got 1 big bunch of stereoisomers, but now you only got 2. Okay, so I'm actually talking about skill number 3 now. Can people skill number 3? Oi? Talking about skill number 3, let's go back to the question because I can't remember what's the compounds. So which one you want me to do? I do C, okay? I happen to choose C I happen to choose C.
Okay.
It is strongly highly recommended that you translate the skeletal first, like what I always say. Can you see that this carbon is actually not chiral? This is not chiral. Because 2 out of the 4 are the same thing, metals. And this is indeed the chiral carbon, right? Now you are supposed to draw your enantiomers. Pretend the question is asking for that. How do you draw it? I need to warn you. Please refer to page. If you remember, there's a formality thing in the notes, my notes. You all refer to page 13. You all don't draw it like that. Your wedge and your dash, they can't be opposite. Because if they are opposite sides, right, like that, you're actually referring to a square planar shape, which is not realistic. You are supposed to draw it as tetrahedral, right? So take note of this error. And then we also go to page 10 of the notes, the same old notes. Another warning, enantiomerism is always a 3-dimensional thing. You don't represent 3-dimensional things by 2-dimensional bonds like that. You'll get 0. Okay, you identify a chiral carbon, okay, but if their question is draw suitable diagrams to show the enantiomerism, this thing will get 0. Because it's 2D. Then how you draw it in 3D? Like that. Wedge means out of the plane of the whiteboard. Dash means into the plane of the whiteboard. So this is one enantiomer. Can. Traditionally, right, the other enantiomer, people will just draw your mirror here and then just reflect. So dash H is pointing down inwards, correct? And your wedge CL is pointing outwards down. Outwards down. Like that. So this is the standard way of drawing. Can? A pair of enantiomers. Remember, wedge and dash must be there, otherwise you get 0. And your wedge and dash must be next to each other. Don't draw like that. It's not like that. Can people? You want another trick I can teach you? You want another trick?
Yes,
This is a standard way of creating your enantiomer.
maybe we can just draw it mirror.
You can, but that's the standard way. If you want to try to be different, I'm trying to teach you how to be different. These things are enantiomers, right? Correct? I haven't dismantled yet. These things are indeed enantiomers. Let's just pretend that this guy is this guy first. Let me just plug out, and then make sure that they're the same thing first. And now the question is, I happen to draw this first. This and this are actually the same thing now, you can see. How do I generate the enantiomer without using the standard way of generating? I just need to choose any two groups on the chiral carbon and swap. Not flip, swap.
Any two what?
Any two groups on the chiral carbon and I swap. I swap the green and the white. And do you realize from the same just now I end up as enantiomers. That's another method.
But how do we know which one to choose?
You can choose any two.
Choose the simplest one.
Yeah, choose the smallest one because it's more convenient.
Oh.
So that's another way to generate the enantiomer. Just swap any two groups of all the chiral carbons. I say all because sometimes there will be two. Sometimes there will be three, but three a bit too hard to test. And so just swap any two groups of all the chiral carbons. In this case, it's only one. So that's what they are doing here. Where's that page where you were asking Joel, then Joel explained to you? The one that you couldn't understand.
Then 5.
Yeah, so you see, you're going to go to page 27, right? It's page 27, focus on this part here, that's what I'm actually talking about. This is the standard way of drawing enantiomers. Standard way, yeah? This is the unorthodox way of forming the enantiomer. What did they effectively do? They effectively swap the X and the Y, right? This is my method, my unorthodox method, this is standard method.
Both acceptable?
Both are acceptable, but I have to warn you all, if you are required to draw enantiomers in promos or prelims, in any internal exam, you get back the script, please check whether the examiner mark it properly or not.
Okay.
Because over the past 4 years in ACJC, every year this type of question, every year the marker will mark wrongly one. Every year they owe my students marks.
Because
Every
they
year,
do it like that.
yeah, because they only recognize it this way. They can't see that this is the same as this. And hence this is also the enantiomer of that.
So they want us to draw it as a mirror image.
Syllabus doesn't say that you must only draw your enantiomers by this way. It just says you need to know how to draw the enantiomers. It doesn't say how you need to draw it. So if you were to swap your X and your Y to get this, and then you draw it side by side and claim that they are enantiomers, they can't mark you wrong either. If they mark you wrong, it means that they are noob lah. They don't know their work lah.
So why don't we just mark off?
Hey, yes, Isha.
Yeah. For this one, right, do you still need to, for the unorthodox method, right, do you still need to draw the mirror? Yeah. Do you still need to draw that thing?
No. You want to draw the mirror is very mafan. The mirror is actually like that. In this case, it's like that.
So that dotted line is necessary or
The
not?
dotted line means it's like that. You are imagining the mirror as like that, and hence you just flip like that. But when you do it an orthodox way, example, this to this, your mirror is actually like that. How you going to draw that?
Okay.
Get it? So that's the unorthodox way, but if you want to use the unorthodox way, please be careful about their marking.
Oh, they got to see the allocation. The isomer.
Yeah, that's what I said. Swap any two groups on all the
the isomers, right?
But in this case, it's previous only one. But generally correct, you say all.
Physical property is one thing, but that's a result of except in the direction. Yeah, so you need
Hey, cannot people, so we are talking about skill C here. Skill 3, sorry.
so that means
We are talking about skill 3 here.
rotate.
Okay, can we go back to the tutorial question? So 18, right? I leave you go and find out yourself, okay? B, C, and D each got one chiral carbon for question 18. A totally full, don't have. Can we go on now? Okay, now we go on to 19, which is horrific. This is skeletal, mostly skeletal. See the number of rings? You get very scared, right?
Yeah.
But there's nothing to scare because I am here.
I'm a hero.
It is what I call the VXY junction rules.
And go.
VXY, bitch.
It always sounds like we only got 15 minutes left.
Let's go.
Okay, now you start panicking when you see this, right? Correct? They are asking for the number of chiral carbons. Pay attention. Okay. Okay, let's start from V. What's a V junction? A V junction is this. An example of V junction is this, and this, and this, and this. Basically, just ignore V junctions. Why? Because they all represent CH2s. 2 out of 4 are the same features. Correct? Ignore V junctions. There, ignore all V junctions if you are trying to find chiral carbons. Hey, there.
Yes.
Okay, let's go on to the cross junction, the X junction. Can you see what are cross junctions? This is a cross junction, this is a cross junction.
So
Most of the time, cross junctions are chiral. Most of the time, they are. In fact, these two cross junctions are chiral. But let me go through with you, justify why they are chiral. Remember, you also look through until you see the first point of difference. So we focus on this cross junction. Why is it chiral? First group is a CH3. Are you paying attention?
yeah.
Second group, we go in the clockwise manner. First group CH3. Second group is a C, which is bonded to an alkyne, right? Third group is a C, which is bonded to 2 other C's, none of which is an alkyne. Fourth group is a CH2. So you agree there are indeed 4 different groups with respect to this guy. So indeed this is chiral. Can. Now this is also chiral. It's a cross junction that's chiral, but we verify it. First group is a OH. Second group is a C triple bond something else. Third group is a CH2. Fourth group is just a C bonded to 4 other C's. 4 other C's. So indeed there are 4 different groups, right? OH, alkyne carbon, CH2, a C which is bonded to 4 other carbons. There are 4 different types of carbons. This one is not a carbon, it's an OH, it's obviously different from the rest. Can people? So this is chiral, can?
It's not all time, but
Is it bonded? This one is bonded?
Yeah, majority of your cross junctions are chiral. Majority are. You still need to check. If you are unsure, just check. A cross junction is a carbon with 4 bonds. There. In a skeletal structure. So this guy here, right? Before this guy here is actually a Y junction. Sorry, I'm talking about cross junction, right?
Yeah.
But this guy here is not a cross junction. This guy here is not really a cross junction. Whatever X lah, can. This is not a cross junction though. It's actually a Y junction. It's drawn like that, correct? This is a Y junction, not a cross junction.
Also, this is in terms of skeleton.
Yes, in terms of skeletal, my VXY technique is based on skeletal structures. Okay?
So cross junction is X or Y? X is it?
Cross junction and X junction are actually the same thing. I just say interchangeably. You know, people, so these two are the only 2 cross junctions, and I always say cross junctions are usually chiral. Just like you need to check if you really got the time, go and check. Go and verify indeed we are chiral, but trust me, most cross junctions are chiral.
What if they have out of 4 groups, right? 2 of
Wait,
them are
later I'll give an example. Yeah. Can I go on to Y junctions?
Yeah.
For Y junctions, you ignore Y junctions that involve high bonds. Why? Because they only got 3 bonds. So, while this is a Y junction, I don't really care about it. This is actually a V junction in a sense, I don't care. Is this a Y junction? Yes, but it's not to be cared about because there's a pi bond there. Then we just skip this skip. This Y junction, it is chiral, Y junction, chiral, 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 and that's all. it's actually 6 chiral carbons. 4 of them are Y junctions, 2 of them are cross junctions. So can Y junctions, please look out for the ones with pi bonds, so ignore them. Ignore them. Get it?
Yeah.
So the V, X, Y, totally don't care about V's. X, just look carefully, but if you don't have time, just assume that all X junctions are chiral.
Why
Why?
within
Because
the
time
X
you should check.
junction?
What?
Why within the X junction there's 2 same groups?
Why?
And not chiral.
Why? Yeah, not chiral.
Huh?
Then it's not chiral.
Isn't that what you're asking just now?
I asked you and then you say wait.
Wait, because I'm going to give you an example. And lastly, Y junctions, just ignore Y junctions with pi bonds. Consider Y junctions without pi bonds. And then I leave it to you to verify that indeed these 3 dots are really chiral Y junctions. Clear? I leave it to you to go and check that all 4 of them are chiral. Alright people? Give you an example of cross junctions and Y junctions that's not supposed to be included, people. So alright, we give you an example here. This guy is a perfect example, no? Do you see 2 Y junctions?
Yeah.
There's no cross junction. This is indeed chiral. I did proven it to you, right? CH3, first group, second group, invisible H, third group, CH2, fourth group, CH2, but don't conclude yet. Carry on. These 2 are different indeed.
Okay.
So the third and the fourth are indeed chiral. Indeed, this Y junction is chiral. And this guy is also chiral. First group H, second group Cl, third group CH2, fourth group CH2, but don't conclude yet. You carry on looking. What?
Is there naming for
No lah. No, don't have. Can people?
Yes.
So I give you an example where she's asking, will your cross junction ever be non-chiral? Give you an example. I'm drawing a cross junction which is non-chiral, okay? I'm drawing a cross junction with non-chiral. And I'm drawing a cross junction which is chiral. And I'm drawing a Y junction which is not chiral. And I'm drawing a Y junction which is not chiral for a different reason. And I'm going to extend later. And I'm just going to extend. And I'm going to draw a Y junction which is non-chiral.
Why is that not chiral?
So you see people, look here, wait, look here. Cross junction, is this chiral? Look carefully. It's not. You got 2 metals stuck to it. It's not chiral, although it's cross. This is a Y junction, but ignore because there's a pi bond. This is a cross junction, but is it chiral?
Yes.
Yes. First group is a Cl, second group is a CH3, third group is a alkene type of C, fourth group is just a CH2. Indeed, 4 different groups. Indeed, this is chiral. Let me carry on. Have you considered this? No, right? It's a Y junction, but it's not chiral.
Why?
2 CH3s.
Oh.
Okay, then we carry on. V junction, don't care. Another V junction, also don't care. How about this Y junction?
Yes.
It is first group H, second group methyl, third group ethyl, fourth group gigantic group.
Oh Jesus.
So this is chiral. So there are 2 chiral carbons. So okay, Ken, I give you examples of cross junctions that are non-chiral and examples of Y junctions that are not involved with pi bonds, but it's still non-chiral. Example, this guy here. So this is a Y junction that's chiral, this is a Y junction that's not chiral, this is a Y junction that's involved in the pi bond anyway, and this is a cross junction that's non-chiral, and this is a cross junction that's chiral. I give you all the cases here. Happy? Learn something new now? So okay, so back to here. I leave it to you to go and check that these 4 Y junctions are indeed chiral. Leave it to you, I don't have time. So Ken, so altogether you got 6 lah, the answer is 6 lor. Shall we go to question 20 now? Oh, cannot. Question 20 cannot. I need to carry on teaching the rest first. Let me just finish out all the skills first. All the skills here. So right, where are we now? We are talking about Wiesel compound, right?
So it can be like
Oh, Wiesel compound. Oh, not yet, not yet. So we are somewhere around 3 and 4 already, people. We are somewhere around 3 and 4.
sorry.
Can you listen? I need to finish up this part, otherwise it's very awkward to carry on. Okay, oi. You all agree that these 2 carbons are chiral, right, just now? So, right, theoretically, you should have 2 stereoisomers. Where does the so-called 2 N rule come about? is similar to how your 2 to the power m rule comes about. Your first chiral carbon, whether it's left-handed or right-handed, is independent of whether the second one is left-handed or right-handed. There are actually 4 possibilities now, right? Correct? And then if you got another chiral carbon, then it's times another 2, you get 8 lah. So you understand where the 2 to the power m rule comes about now? Can? So based on that rule, right, this guy here supposed to have how many stereoisomers? 2 to the power 2, right, which is 4, right? But you will realize that, yes, I got my cis. Okay, let's just fix this. Red is the reference. Or maybe I just draw on the board because I don't have enough models to show. So I go to this whiteboard. So I use cyclobutane as an example. This is up, right, people? This is, the other case is down, correct? The third case is up, down. And the last case is down, up. This one was the one that I proved to you they are enantiomers, correct? Because both of them lack an internal mirror plane. So the mirror image of each other won't be the same as themselves. Got it?
Yeah.
This guy here is indeed the mirror image of this. But do you realize it's actually the same thing? Yes. Because of the internal mirror plane cutting through here. It's just a matter of flipping. Let me just show it to you. I'm going to dismantle this. I think I got a cis anyway. I got a cis ready here. Let's flip the damn thing. Then it's the other one. Why is it the same? It's because of the internal mirror plane cutting through like that. Okay. Now let me define this thing called a meso compound. A meso compound is a compound with chiral carbons, but because of the presence of an internal mirror plane, it will end up non-chiral. In other words, its mirror image, which is this, will be the same as itself. Can? So theoretically, while you have 4 stereoisomers because of 2 chiral carbons, you end up with only 3 stereoisomers. The meso guy, which is the cis guy, and the 2 trans, which make up a pair of enantiomers. Okay, so all together you got 3. Theoretically 4, based on P and C. Up, down, up, down. Theoretically 4, in actual fact, only 3. This, which is the same thing, and this 3. Got it?
Miso is basically just enantiomer with internal planes. So you know, like miso soup.
No, miso means is a compound with chiral carbons within it, but
because there's no
But
internal plane.
there is.
Because there is, so then it's...
Its mirror image will be identical to itself.
Okay. So if it's not an enantiomer, it will be a miso compound?
See the box to the ears.
Not always.
Not always.
Yeah, see the cis.
Then in which case is it like not an enantiomer?
Actually,
These 2 different compounds.
what you are saying, you are betraying a very bad misconception. And enantiomer is a relational term.
So the first one is
Oh.
like the second one and then the third one is like
So
that.
like,
And then
what do you mean by relational though? Like is it independent?
You hate chem because of me?
yeah.
You say you hate chem what? Organic chem is like that. There's a lot of visualization, mental visualization. Physical chem is another type of torture, correct? You need to really analyze the question properly, right? You need to understand the maths behind it also, whatever lah. Organic chem is something else to put together. Wow, she like shell shock in the middle of a battlefield. Cannot now.
Wait, no, so what do you mean by relational?
Like I am a son. Son of who? Son of listener? Or son of a peasant?
Okay.
Son of what?
So basically it's an orientation
I said I
like
am a son. I am the son of who?
The son of the world.
But it's a son of Singapore, it's not the son of Singapore. The son of who? I am the enantiomer. Enantiomer of what?
Oh.
It's relational.
Okay.
It's like saying I am the father. Am I the father as in a blasphemous type of father? Or am I the father of my son? But the boys are not even married.
Oh.
Understand what I'm saying or not? And I'm not a father in the Catholic priest sense also. So exactly what do I mean when I say I am a father? father. A father to what lah? A father to all my children, that's it. But I never say, then how they know?
It's Winston, obviously.
Can or not, people? I am a brother, okay? I am a brother to who? Your biological brother or your brothers in the Catholic order?
A friend brother.
He's a brother to
Yeah, you need to define. Brother with respect to what? Okay, with respect to what? Get it? So can I summarize today's lesson?
Yeah.
Basically, I don't summarize the cis trans, okay? Cis trans is easy to understand already. But in entomorphism, you realize it actually overlaps with cis trans, right? Correct? Both are trans, while this is cis. Okay? There's actually an overlap. Like what I wrote here. Oi, read here. Cis trans and entomorphism sometimes overlap together one, like especially in your cycloalkanes cases. Okay? And then in summary, right, whether you want to check a molecule is chiral or not, you look out for internal mural plane. If there is such a thing inside the molecule, it means that its mirror image will be the same as itself. Clear? Know how to look for chiral carbons, okay? Know how to identify what carbons are chiral, and be aware that while you may have chiral carbons, the entire molecule might have an internal mirror plane. Its mirror image will end up as itself, as the same as itself. We call this a meso compound. Clear?
Yeah.
So the recurring idea that goes over and over again is, if I say that something is chiral, it just means that it doesn't have any internal mirror plane. What's the implications? The mirror image will be the same as itself. Can people? The bottom line is, whether you are checking whether an atom or a molecule is chiral or not, you look out for an internal mirror plane. If there is, it means that it is non-chiral, its mirror image will be the same as itself. If there isn't such an internal mirror plane, it means that it is chiral, its mirror image won't be the same as itself. We call it enantiomerism. Yes. Clear? Cis trans is not enantiomerism. What?
Is where the image is not the same.
Oh my god. Hey, if I relax,
How can the mirror image be not the same?
look at the blood.
Can you see that this is the mirror image of the other one? Can you see?
Yeah, I see.
Can you see they are not the same thing?
Yeah, I see that they're the same thing.
How can it be the same thing when your black overlaps with your red?
Event. So like when you look at the thing, right, you can only move it this way. You can't like flip it anywhere else. You
can flip it. It's that you can't break any bonds.
Wait, can I out close? Okay, let's go. Okay, alright, let's go.
It's a,
Look,
it's a mock-up.
this is the mirror, right? But these two are in the real space. They are mirroring each other, but when you bring them together, the white is not green and the green is not white.
It's not exactly same.
It's like your hands, like that. It's not the same. Again.
Yay.
So you call that enantiomerism?
Yes, there's no internal mirror plane in anywhere here,
How are you
agree?
gonna make an internal?
You don't want to make the internal.
No, it's not that you don't want, there isn't any internal mirror plane in here. You try to cut through here, no, it's not an internal mirror plane because green is not equal to black. You cut through your plane here, your red is not equal to black. There isn't any internal mirror plane inside this. So when you create the mirror image with this, it won't be the same thing, you see, like what she supposedly proven to you, but I really tried 100 times to prove to you. Using exactly the same words. They are not the same thing. Your red, your black, and your
I get
green.
this part, I get this part.
Yeah, get it?
Next.
So while you may have chiral carbons here and here, while you have chiral carbons here and here, people, hey, Benjamin, can you pay attention or not? While you have chiral carbons here and here you have an internal mirror plane, right? Its mirror image which is this will be the same as itself, get it? Can you see that this is the same as this? It's a method of flipping, right?
Dude, that red line thing means it's going down. That
it
one
means it's going to your face.
Yeah. The down one? No.
And this is not the same as this
The
because
dash
there is no
line.
internal mirror plane in any of them. So the mirror image which is the two of them won't be the same as each
Yeah,
other,
that's
right?
So yeah. So that one's going into the white, that one's going out. So it's like the same compound. It's just that, okay, imagine this, right? So this is my compound, right? Then those two
Yeah.
Sounds weird.
Well, how do you know
this
whether it's a
one is
miscible?
going
That's
into
an important thing.
into the
When there's an internal
and this one
mirror
is going out like this. So, but even if
It's saying the correct
they are
things,
the
but
same compound,
it doesn't
it's the
help
same,
anybody
it's the
find
same
out whether
atom.
something is miso or not.
Imagine you see it
It's
here.
correct, but it's not
It's the same
helpful.
atoms here. It's just that it's facing.
Oh my god.
It's the same atoms, right? It's just that it's facing. It's just going in different directions. So like it has but because
Which is
right,
the
if
key
you look at it, because it has two like that. Like let's look at the left.
That's why I put it in bold, keep it in caps, right?
It's both
It's
like
the
that.
central idea behind all these
Like that.
things.
So right, when you
And it's
put
also
the
the
internal
link between this and
that
this,
thing
okay?
right, that is machine
Since,
thing.
because it's
It's the
cis
same
and because your
compound.
two groups are the same, that's why you got internal
Right?
mirror
So it's
plane.
miso because
When they are trans,
if you
even
have
if they are
an
the same
internal
substitute,
plane, then there is miso
your
compound.
internal mirror plane is destroyed. So you end up is
It is
identicalism
symmetry,
here.
yeah. Miso is if there is symmetry. If you
Cis
can
and trans
find
are-
symmetry
cis,
in
trans
the
and
compound,
identicalism are actually
then it's
related
miso.
one.
If you cannot, then it's symmetry.
They overlap here, like what I'm saying, point number 8. Cis trans identicalism
Yeah,
coincide in the cases of cycloalkenes with at least two. Yeah, your something was your saturated sp3
Wait,
and
no,
realized
we
atoms
cannot
is
say
why I
that
think
if it's not
for
miso, it's enantiomer. What's enantiomer?
What if this thing was to be flat?
Yeah.
Would you have such a case?
It's always cis. Wait, so confirm miso is always cis, right?
Huh?
Is miso always cis? Confirm only.
It's not always cis.
They don't agree.
If you were to look at your page, hello, can I just go through one last line before I close out the lesson? Go to your notes, right? Hey shit, you all got maths lesson now. She's gonna kill me, go.